So today we'll be looking into uh, a problem that is much more complex, and this problem deals with rotational dynamics. In this problem, we have two cylinders, one on top and one on the bottom. The, the top cylinder is anchored to the ceiling by two strings, and it's from this top cylinder we suspend a cylinder below. Both these cylinders are free to move. The top cylinder moves this way, and the bottom cylinder moves in the opposite, rotates in the opposite direction, right? And while the cylinders are rotating, the string on the top cylinder unwinds, and therefore the bottom cylinder descends towards the floor. Both cylinders have mass equal to m and radius equal to r. So our task today is to find out the the tension in each of these strings, so that's, on the face of it, it appears like a daunting problem, but we will try to solve it as best we can. Okay, so now one of the things we know is that the force on the top cylinder, okay, equals 2 times t, right? Because uh, there is a tension acting downwards on the top cylinder, there's another tension acting downwards on the top cylinder, and since both these strings are symmetrically placed, both tensions are the same and equal to T each. So the total tension equal to 2T. Right? So now, we know that the torque on the upper cylinder is the force times the radius. The torque on the upper cylinder we will call the tau on top, okay, equals 2T times R, okay, and that should be equal to I on the top for the top cylinder times alpha, okay, where alpha is the angular acceleration. So since we have a cylinder on top, so the moment of inertia is half times m times r squared, and alpha equals the linear acceleration divided by r. Okay, so it's the linear acceleration divided by r. So here, if we plug all these things in, 2 times t times r equals half m r squared a divided by r. So one of the r's cancels out here, the other r cancels out here. So in this particular situation, the acceleration here, with the linear acceleration at the periphery of the top cylinder, equals 4t divided by m. Okay, and so this is the acceleration at the periphery of the top cylinder. Okay, now what happens here is that we'll momentarily set that aside. Okay, we will momentarily set that aside, and we will do the same computation for the bottom cylinder. So for the bottom cylinder, the tension acts upwards this way, the tension in the other string acts upwards this way. So we have the very same acceleration for the bottom cylinder. Okay, now the thing here is that we will talk about a relative acceleration. Okay, so here the reference frame is fixed on the center of mass of the bottom cylinder. So here we when we do that, the relative acceleration, the relative, let's call this linear acceleration, is found using the same formalism that we used here. Very same formalism. So we have the tau at the bottom equals 2 times t times r, because r is the radius of the bottom cylinder, equals I bottom times alpha. So this equals half m r square times alpha, or rather we will write alpha equals a bottom by r. And so the one of the r's cancels out, the other r will also cancel out. So the relative acceleration, okay, so the relative acceleration at the bottom, okay, equals 4t divided by m. Okay, so now the thing here is that if we look at the free body diagram, right, if we look at the free body diagram, okay, on the bottom cylinder, we find that this is the weight acting downwards, okay, and here are the forces acting upwards, so that's 2t, right? So since the cylinder is moving downwards, so and we'll just label this at as the bottom. So since the cylinder is moving downwards, we can write the Newton's law of motion as mg minus 2t equals m times a total. Okay. Now, so what is a total? Okay. So a total is the relative acceleration of the bottom cylinder plus the acceleration of the top. Okay. So a total equals 4t over m plus 4t over m equals 8t over m. Okay, so that's what we get. Okay. So when we plug that in, mg minus 2t equals m times 8t over m. The m's cancelled out. So mg equals 8t plus 2t, or we can write this as mg equals 10t. Therefore, the tension in each string equals mg divided by 10. Okay, so that's the correct value of tension in each string. So let's review this. Okay, just so we understand this properly. What we found was the torque on the top cylinder, and that equals 2t times r. So that equals the moment of inertia times the angular acceleration. For a cylinder that is rotating about its long axis, the moment of inertia is half mr squared, and the angular acceleration equals the linear acceleration at the periphery, okay, divided by r. Okay, so when we take all this stuff, we take everything here and plug that in, right? So when you plug that in, 2 times tr equals half mr squared times a divided by r. So the linear acceleration at the top, right, will make this at the top. Okay, so equals 4t divided by m. So that means that if the portion of the string here is accelerating downwards by 4t over m, right? So So now we fix a reference frame on the bottom cylinder, okay, and then at the center of mass. So the reference frame is also moving with respect to the floor. So in this reference frame, what we do here is that the the torque is the same, is equal to 2t 2t, that's the total force, times the radius, right? And that equals I times alpha. The moment of inertia is the same, and alpha is the relative acceleration, okay, in this frame of reference, divided by r. That is a relative linear acceleration divided by r. And so we come up with the very same expression. Okay, so now in order to find the true acceleration of the center of mass, right, what we have to do is we have to find the acceleration of this portion of the string, because the the top cylinder is unwinding, plus the acceleration caused by the unwinding of the bottom cylinder. So when we do that, the total acceleration is 4t plus divided by m plus 4t divided by m equals 8t divided by m. So if we draw the free body diagram here, okay, so mg minus 2t, okay, is the net force, because mg acts downwards, that's the weight, and 2t is the force acting upwards. So the purposes of writing the Newton's law, so this bottom cylinder is assumed to be a point object, okay, but I've written it this way just so you can understand it. So mg minus 2t equals m times a total, and a total is 8t divided by m. So we cancel out the m's here and rearrange the terms. So we get mg equals 10t and t equals mg by 10, mg divided by 10. So I hope this particular chapter, interests you further in determining how physics problems should be solved, and it gives you a sense of encouragement. If you like this video, please press the like button and subscribe to this channel. Thank you.